Good morning, everybody. Good evening.
Good
So,
evening.
okay, good evening. I was asking that whatever your doubts in your quiz one examination paper, you can ask first of all. Okay, then we will continue with the week six content.
So we can
I have.
continue with.
What, Mayur?
Sir, I have one doubt in that question paper, sir. So I do not remember the question number, but the question is given a square matrix, which of the following are defined? And they have the options are a plus a square.
Okay. This one, right?
Yes, sir, this one. Uh, Here, why a plus a is not defined? Because both are square matrix and we can have element wise addition, isn't it?
Here it is given that are all only valid when m is equal to n. Means in other cases when m is not equal to n, then it should not be there.
Valid often.
So if it is not a square matrix, then it should not be defined. But here you know that when we add two matrices, so if they are not square, still we can add them. If they are not square matrix, then still we can add them. A square can only we can find when we have square matrices.
Yes,
Oh,
we
okay,
Other
will
sir.
than that, we
determine.
can't.
Then what about
So
the
a
last one?
dot last one is saying that c times of a you can find out. Means you can multiply any matrix of any order with c, so you can find out that value. It doesn't imply that you need to have only square matrices in that case. Even if it is rectangle, you can still, if you multiply by c, so it will be c2, c3, c like this. Okay.
Okay, sir. Okay, I missed out that word only.
Okay. Any other question? Anyone else?
Sir, can you
Quiz
just
one cleared.
share the link of this PDF?
What?
Sir, is this PDF available on the dashboard, sir, for to download?
This question paper.
Yes, sir. Yes, sir.
I think they have.
It is in your portal. It is already available, I think, there. On your portal, it is available.
Ravi is available.
So no other doubts in quiz one?
I'm just checking the papers.
Okay, you can check. Okay, anybody else having any doubt related to the quiz one in any question?
So this question, sir, this alpha beta 2.
This one,
Yes.
you want solution for this? Okay.
If possible, could you give the solution?
Okay.
Yeah, it would be great if you can give the solution also.
Okay. So we are given 103 and minus 240. This is our matrix A that is given here. Okay. And it is given that alpha beta 2 is a solution. Means if I multiply it by alpha beta and 2, so I will get my solution like 1 minus 2. Okay, so now it is in the form ax equals b, right? So we know that all the solutions of ax equals b will be the solution of rx equal b. This b dash, sorry, that is derived. So it is the row echelon form of that matrix. So we can write it as like this: 103 vertical bar 1 and minus 240 minus 2. Okay, so now I can apply R2 plus 2 times of R1. So what will I get here? 103, 1 over here, and 0, 4, and 6, and here 2 times R1 if I add, so it will be 0. Okay, now if I divide R2 by 4, so what will I get? 103 here, 1 here, and 0, 1, 1.5, and 0 here. So if I know that now this equation is like this, if I rewrite it in the form of matrix 1, 0, 3, 0, 1, 1.5 times alpha beta 2 will be equal to 1, 0. Okay. So I can write these, I can do the multiplication on the left hand side. So I will get alpha plus 3 2s are, okay, and below it I will get beta plus 1.5 times 2, 1.5 times 2 multiplication it is, okay. So you will get it will be equal to 1 and here it will be equal to 0. So you can get the value alpha plus 6 is equal to 1 and alpha will be equal to minus 5. Similarly here you can find the value of beta. Beta plus 3 is equal to 0 and beta will be equal to minus 3. Is that clear?
Sir, I did the directly. I did the multiplication. I got two equations without reduction. I straight away,
Yeah,
got
that's
two.
also fine.
Yeah, I mean, yeah, yeah, I got
That
the
is
same.
also fine.
Thanks.
Because I already told that even if in the reduced row echelon form you will get the same answers and as well as in the original form you will get the same answer. So wherever you find easy, then that's okay. Okay. Anyone else having any other doubt? Okay, let me check. See the questions, then ask if you have any doubt in them.
So can you solve this one?
Yes, this question.
Okay. Two vector spaces are given, subspaces, and it is saying that the previous one or this one only.
This one. Previous one is okay.
Okay, in this one you have to find the set of matrices which spans W2. So what is W2 here? So we will find for W2's basis firstly. Okay, means the compulsory vectors we will get. So from here, A plus B is equal to 0 and C plus D is equal to 0 is given. So here I can write A will be equal to minus B from my first equation, and from second equation C will be equal to minus D.
Correct.
So what is the general form that is given here? A, B, C, D. So I can replace A
A minus
with
S.
minus B, okay,
Minus
and
C.
C with minus.
Correct, correct.
Okay. So now what I can do, I can uh, write these variables outside these matrices like this: minus B times or B
One.
times minus 1 here, 0, 0 here, plus D times um, 0, 0 here, and minus 1, 1 here.
Correct.
Right?
Right.
So it means it's a basis must include these two, any multiple of these two, or maybe these two. So even if I can also define it as minus, I can also write in other way that let me write it again, that B is equal to minus A.
Right,
Okay,
sir.
and C will
Basically,
be equal to,
okay, okay.
okay. So
So B6 and B7 will be there, right?
what? 1 minus, sorry, A minus A will be here, and minus C, sorry, C and minus C will be here. So if
Correct.
you do now, so you will get here, let me do this.
A one
A
minus one
here, minus,
minus one.
okay, and this is plus, okay, and this is plus here, and this is minus
Correct.
1. So means these two are to be needed to be in the basis. So these two make the basis, and any other vector if we have, then it will also span. So you can see B6 is this and
B6
B7
is
is this.
this. Correct.
Means B6 and B7 are needed. Okay. Other ones, if you are going to add, then it is not going to make any change, but it will not be a basis then. It can span this W2, but it will not be a basis. Okay. Basis require uh,
So this is the minimal spanning, right? Basically.
minimum Yeah, minimal spanning it is. So for minimal spanning, we require these two matrices. So
If
B
we
and
add everything
six and
else,
seven are
it won't be any minimal spanning anymore.
yeah. So these okay, we have done so far. But now for this case, this is a span for all matrices,
Correct, correct.
all 2 by 2 matrices. Okay, it can span all the 2 by 2 matrices set. So you can see here, if it is spanning all of them, then these are also get covered. These two situations. So it will cover this part and this part as well, and all the other remaining matrices will also be there. So it is also spanning this W2 because it is spanning all the matrices. So it is also spanning the W2.
But sir, those combination would also result in something which we don't want, sir. So will we consider that?
Yeah, but it is not a
Exactly.
basis. We are not finding the basis. We are finding only spanning sets. Spanning set we can include any other vectors as well. There is
If the
no foundation on it.
if the if the question is about W2, we are given two conditions of W2 formation. So how can we say that spanning of B1, B2, B3, B4 will be correct?
Okay,
Yeah, because
you have
here it's given, right, basically. But if
That
there would
span will
listen.
contain it. That is not an issue, sir. But the thing is, can we compare them?
Listen, I will compare this. B2 will be 0, 1, 0, 0, and B3 is equal to 0, 0, 1, 0, right? And B4 was 0, 0, 0, 1. Okay, this is. So you want to form all these type of matrices. Okay, so you can see here, if I want any linear combination of these to make all these type of matrices, so what I can say that uh, B1 times my first matrix, not B1, let's say X times or A times my first matrix, okay, minus A times my second matrix, okay, and C times my third matrix, and minus C times my fourth matrix. So now if you add, you will again get the general form, that is A minus A, C minus C. Okay, so their linear combination is also covering all these type of matrices. If you include the right coefficient in front of them, then it will also uh, span this set.
Okay,
It is
we
actually
are just
spanning
checking
all
whether
the,
it can span or not. Maybe it is producing extra. We don't care about it.
no, yeah, we don't care about that thing. Okay,
So our options is not about like we have coefficients as something.
yes,
We
so
just
on
can
coefficient we
imagine
are,
imagination only by just seeing that bases are there.
yeah,
So we
it is just an observation based. You can simply think that it's span of this uh, B1, B2, B3, and B4 covers all the 2 by 2 matrices. All 2 by 2 matrices it is covering. So it automatically includes any other, if you are applying some equations and these type of relations in them, then it will also cover them. It is directly observable. So you don't have to worry about these condition when we are spanning all the sets, all the matrices of 2 by 2 we are already spanning. So it will also cover these specific cases. So then there is no need to go into depth like this. But if you want, then you can see. Okay.
okay, sir.
Any, okay. Any other query?
So
So
that
next
W1
question
and
on
W2 one.
W1 intersection W2 or
Yeah, this one.
Yes, sir.
yeah, this one
below
W
one.
section W2.
Oh, okay, this
Yes, sir.
one.
This one. There was that intersection.
Okay. Intersection means both the conditions should be satisfied. This first condition and this one. I can write this W1, rewrite. Okay, what will that be? All those point x comma y comma z for which x is equal to 0 and y comma z and x comma z belongs to real number. Or this, you can omit this y comma z. Can I rewrite it like this? Is there any problem in this?
No, sir.
It will include all those points in the three-dimensional points or three-dimensional the three components vector for which the first component is 0. So I write this like, okay, so I got one equation from here that is x is equal to 0. Now in the below one, it is also taking all those vectors for which their x component plus y component plus z component is 0. So you can write this equation as well, x plus y plus z is equal to 0, right? So now if you represent it in the matrix format, what you will get? 1, 0, 0. Okay, and here you will get 1, 1, 1 times x comma y comma z will be equal to 0 comma 0. So it is saying that, okay, now I have to find a basis for this. So simply reduce this A matrix. So I can write R2 minus R1. So what will I get? 1, 0, 0, 0, 1, 1. Okay. So this is my pivoted element. This is my pivot element. So two columns got, one is independent. So I can write the dependent variables in form of independent. So first equation is nothing but x is equal to 0. Second equation will be x plus y is equal to y plus z is equal to 0. And means y is equal to minus z. Okay. So if I find any standard basis, so I have only one independent variable. So give this variable value 1. So x value is 0 already there, and z value is 1 we gave, and y value we got as minus 1. Okay. Or you can do other side, that give z value as minus 1, and this will be positive 1. So what you will get here, 0 times 1 and minus 1. This can form the basis for, this only vector can form the basis for its solution. So here it is. We can see. Now comes to the first part. Why is this?
Sir,
Okay, why is this first?
so this like this
What?
z, so you took z equal to minus 1, right? In this
Yeah.
Z equal to
Okay. You can, let's see. Z is 1. Okay. Take the value of z as 1. Okay. So now what you will get the value of y? You will get
minus 1.
minus 1. Okay.
But
So what is
just
your
wanted to ask, sir,
that have,
why did you take z equal to 1 as such?
because we have only one independent variable, so I can give any value to this
Okay, okay.
independent variable. Means it can take anyone, any value.
So I can take
Okay.
two also,
But
right,
the
sir?
other, yeah, you can write 2 here as well. And if you want, suppose you are having two variables, two independent variables. Okay, so what you can do, you have to give first variable as a constant value other than 0. Okay, and the all other independent variables will get the value 0. In next case, what you will do, this will also get 0, but the next variable will get some value that is not equal to 0. Some any other thing, p might be, and other will get 0. So in this way we go on. Just for standard basis, we mostly use this one. Okay, so that's why we use mostly 1. But if you look that you got this vector, if you multiply this by minus 1, so you will again get this 0, 1. This is nothing but this. Okay, and even if you put here minus 1, or if you put 2 here, so what you will get here? You will get 0
0, 2, minus 2.
minus
Understood.
this one.
Mhm.
Okay,
It,
so
it
it
can
is also
come
a
out in
multiple
this
of this.
form. Yeah, yeah, yeah. It's okay. It's a scalar
These are
multiple.
multiple of one another. Yeah, these are just scalar multiples. So its span of this vector actually takes all the scalar multiples, all the linear combinations of this vector. So it will also include this. If we have this, so it can include this. Okay, and if we are having this as basis, so it will also include this. Because its linear combination, we can form this, and from its linear combination, I can form this. So there is no boundation on using these variables like this, but standardly we use one. Okay, so that we write. Here you can see it is exactly matching with this. So means this part is enough. We can put beta is equal to 0 for all cases, and this will again uh, include all these points. Okay, but if you look here, it is nothing but minus times this vector, first vector. It is given alpha times v plus beta times minus v. So if I add these two, so what will I get? Alpha minus beta times v. It is nothing but a linear combination, or a scalar multiple of v, where alpha and beta both are real numbers, right? So alpha minus beta will also be a real number. Okay, so that's why it is covering all the points in this form. Okay, Means I can omit this alpha minus beta and I can replace it with k times v, where k is a real number. This is the same thing. When we write span is also the same thing for single vector. If we have only one vector, so its linear combination is only possible in this case when we do the scalar multiple 0, 1, minus 1, like this, where k belongs to the real number. Okay, is that clear? Okay, so now let's move.
Sir, can you explain that union part also? W1 union W2.
Okay, okay. Intersection is there, so dimension we have to find out. So I think this is clear that dimension will be 1.
Yes, sir.
We have one independent vector only. Okay, so next is okay, union. So for union, if it is a subspace, if W1 union W2 is a subspace, then it must satisfy that W. Let's take some else.
Excuse me,
U
sir.
and V
Excuse me, what we are solving, sir, is the paper or what we are solving?
paper at the examination.
Excuse me. Okay, okay, okay. Thank you.
V1 and U, suppose both the vectors belongs to W1 union W2. Okay. So it can either be in W1 or it can be in W2, these vectors, okay, or they can be in both, okay. So these two are vectors, then V plus U also be inside this W1 union W2, okay. Means it should be at least in W1 or W2. Any one of them, it should be at least in, okay. So suppose I took a point from my first vector, that is 0, 1, 1. Suppose this is my vector, okay. Now I take a second vector, it is u, okay. Now I am taking second vector, so uh, let's take it as -2, 1, 1, right. And if I add both these vectors, so I will get -2, 2 and 2. So you can see that this is not going to belongs to W1. It can't belong to W1 because its x component is not 0. Okay, as well as it cannot belong to W2 because x plus y plus z in this case is 2. It is not 0. So their linear combination is not matching with or is not inside the W1 union W2. Okay, so that's why it is not a subspace. Yeah.
Can you just explain one more
Yes.
time, sir?
Okay. So it is asking, we are going to find out firstly this W1 union W2. So it is nothing but all the points that are inside W1 as well as, sorry, W1, and we are going to include these points also that are inside W2. Okay, so inside W1 are all there and all the vectors inside W2 are also there. So suppose if I take two vectors that are inside this W1 union W2, so their sum should also be inside this W1 intersect, oh sorry, union W2. So I took my first vector u as here, that is inside W1. If it is inside W1, then it will be inside this W1 union W2. Okay. V2 I took inside W2. So if it is inside W2, then it is also be inside this W1 union W2. Okay. So I did their addition and I got this vector as result. So it is not even inside this W1 and not inside W2. So that's why it is not a subspace. Is that
Okay,
clear?
sir. Yes, sir.
Okay. Anyone else having any query?
So basically, in this union thing, we will always say, for example, in these kind of examples, we'll always check for if V plus U is belonging to W1 union W2 or not, right?
Yeah. Yeah, yeah. Or one thing you need to keep in mind that most of the times, not always, but most of the time, W1 union W2 is not a subspace. Most of the time you will get. Okay, unless it is a subset of this one.
Sir, if
Okay,
Sir,
if it is a subset.
so, sir, like say for example, since you have assumed real number in this thing, that's fine. Say for example,
Yeah.
I am adding these two, right? Zero y z and x y z. I'm not assuming any real number in this case. Okay, so I will
Okay.
have x comma two y comma two z, right?
Yeah. Yeah.
So
Right.
I can go in this manner also, right?
You can go in this manner as well because it is including this x here. Okay, so there are some. Sorry. What is this? Yeah, x component should be zero to belong it to the first case. Suppose x is not zero, then it will
Then,
not be inside
then
W1,
it will,
right?
then it will not be in
Okay,
W1, correct?
and it is also, yeah. And if x plus y plus z is equal to 0, it doesn't imply that x plus 2y plus 2z will also be 0. It doesn't imply this thing. It can
Okay.
be other than 0 as well. Okay.
Okay. So
So
okay.
you can
So
take some example.
at least one condition has
Yeah.
to be
Or
satisfied basically in this case.
yeah, at least one condition it is to be satisfied.
Or right, or okay.
Okay. So from first equation you can see x is equal to minus y minus z. But in the second equation you can see x is nothing but twice of minus y minus z. You can write like this, and x is other than 0, it is not 0. Okay. So it is not possible when it is non-zero value. If x is non-zero value, then if x is equal to minus y minus z, then its twice cannot be equal to x. It is only possible when x is 0. So that's why if x is not 0, then it will not belongs to any of them. Okay, it will remain outside. Okay.
The last question, sir.
This one.
Yes, sir. Means that has two
Okay.
sub questions. That
Okay.
question I got
So in
wrong.
this, okay. Okay. It is saying that a determinant of a b is 0. So what I can write, determinant of a b is nothing but determinant of a times determinant of b, right? Okay. So if determinant of AB is equal to 0, then means determinant of A times determinant of B is also 0. So means either determinant of A is 0 or determinant of B is 0. So firstly, let's think that determinant of A is 0. Then let's find out determinant of A. Suppose I am finding with respect to this third column. So 1 times 0, 1, 1, 0 plus alpha times 1, 0, 0, 1, right? So what will I get here? Minus 1 plus alpha is equal to 0. It implies this. Okay. So alpha value is 1 here. So if value of alpha is 1, then determinant of A will become 0. And if determinant of A is 0, then this determinant of AB will also be 0. Okay. Now check for the condition number 2 when determinant of B is 0. Okay. So I'm expanding again it with respect to the third column. Okay. So 1 is here, 0, 6, 6, 1 is here. Sorry. Where is this? Yeah, 1 is here. Okay. After that, we can write beta minus 1 here, and it will be beta minus 2, 1, 0, 0, right? So here you will have minus 6. Here you will have beta minus 1. Okay, it is bracket times beta minus 2 is equal to 0. Okay. Determinant of B is 0. So this one. So you can expand this. So it will be nothing but beta minus 3 beta plus 2 minus 6 is equal to 0. Okay, and if you do beta minus 3 beta minus 4 is equal to 0. Using factorization method, I can write beta square minus 4 beta plus beta minus 4 is equal to 0. I can write it again, beta times beta minus 4 plus 1 times beta minus 4, right? So from here I got beta minus 4, and here I got beta plus 1 is equal to 0, right? So either the beta value is my 4 or minus 1 from these two values. Okay, if I equate this equal to 0, so I will get beta equal 4. If I equate this with equal to 0, so it will minus 1. So any of them condition is possible to make the determinant of this matrix as 0. Okay. So here -1 is not in the option, only 4. So this option is also correct. Okay.
Yes, sir. And second one?
Second one is here. Okay. In this one,
Yes,
alpha
sir.
is 3 and beta is 0. So we have to find out the determinant for this. So as we know that A is also a 3 by 3 matrix and B is also a 3 by 3 matrix. Okay, first thing it is to be noted. Next is alpha value is 3. Let's do it after that. Firstly, let's check determinant of minus beta transpose, okay, times determinant of A square times determinant of B inverse. What is this one? Beta transpose is nothing but it is also a 3 by 3 matrix. Okay, and the determinant of beta transpose will be same as the determinant of beta.
Yes.
Beta or B? B it is, not beta.
BB.
It is B,
B.
not beta. So B is minus B is determinant, and if -1 is multiplied in B, so 3 rows are there, so 3 times it will be multiplied. So it is nothing but 3 raised to the power 3 times determinant of. Next is
Yes.
this. So this is nothing but determinant of A the
Whole
square.
square.
Okay. This is determinant of B inverse. It is nothing but
1
determinant
by
of
determinant.
B
Whole
inverse.
inverse.
So it will be minus determinant of B, right? It will be a determinant of A square, and it will be 1 by determinant of B. Okay, so you can cancel these two things. Okay, make sure beta is not 0. Okay, so this will be some positive value for the determinant. Here we will have, so that's why we can cancel these two things. Otherwise, if beta is either 4 or -1, then it will 0 and we can't do this thing. Okay, this is not possible in that case, but now it is possible. Okay, next is minus alpha minus A is determinant of A square. So what is A here? A is there, and here it is given 3 value of alpha. And the last time when we found the determinant, so the determinant was alpha -1, right? So if alpha -1 is the determinant, so what is alpha? 3. So determinant will be 2. It will be -2 square. 2 square is -4.
Sir,
Yeah.
sir, I got the answer right, but I minus is taken as a -1q, but it is only given minus B transpose. Why we done -1q?
It's a 3 by cross 3 matrix, na? You are multiplying -1 to entire matrix.
It does not say -1 we are multiplying. It says only a minus, determinant of
So I am
minus.
writing minus b raised to
It
t
is
as
both,
-1 raised to
both
3 multiplied by b raised to t. That's what I am writing. It's equivalent.
both are listen, both are equal. If you're multiplying -1 to B, it is also equal to -B. Okay,
Okay,
this
sir.
is
I
same.
got the
That's the problem only.
Sir,
Anyone else having any
sir, that -1 raised to n into the matrix is the property, na? So that's what.
Yeah, this is a property that if you want to find out determinant of k times of matrix A, so it will be nothing but k raised to the power n times determinant of A.
Yes.
Okay. Anyone else having any other doubt in any other question? You can see again.
Sir, please move to the week 6, please.
Week 6, yeah, we will go. Just let me check. Nothing's remaining. So let's move to the week 6. So in week 6 till now we have studied a lot of things. That includes this linear transformation that I said it is nothing but a linear combination of these things. Okay, anyone else having if any doubt, then you can tell me now. Otherwise, I will continue to the week 6.
Continue, sir.
So we have seen the linear transformation so far, and I told that two properties are to be satisfied for any linear transformation. First is this, and second is this. Okay. After that, we have studied already that image of zero vector of this V will be equal to the for linear transformation. If we apply on the zero vector, so it will be the zero vector of the codomains vector space. Okay. After that, let's move image. If we want to find out image, so we can use standard basis or any other basis in order to get the image of any point. Okay. After that, we can find out the general form of transformation using these bases. Next is injectivity and surjectivity. Injectivity means all the points inside the range space have a uh, unique pre-image in the V vector space. Okay, unique pre-image is there. Okay, 2 points can't have the same image. Means if I want to find out all those vectors which are going to whose transformation is nothing but a zero vector, so it will be unique. This V will be unique, and that is zero vector of V. If has more than one vector is there mapped to the zero vector of W, then it will not be injective. Next is surjectivity. What is surjectivity? That codomain space is equal to the range space. Codomain space is equal to the range space. Means all the points inside the codomain are some image of some points inside the domain. All the points in the codomain. Okay. So yeah, this is done. Next was null space. So what is null space? Null space is a set of all those vectors for which its image is zero. Vector of W vector space. Okay. And what is image or range space? Range space is nothing but it is a set which includes all the images of all the V's that are inside our domain. Okay, all those points that are inside its images it will store in the range space. It will store only the images. Okay, and in kernel it stores the points itself whose image is zero. It stores these points in kernel. Okay, basically you can say that range space is nothing but a subset of W vector space, and range space it is range space. Okay, and kernel is a subspace of vector space V. Now let's move.
I have a doubt in that earlier
Which one?
point, this point.
Yeah.
Range space and image space.
Yeah, these two are same. Range space and image space. It is
Sir,
kernel.
please explain one time more.
Okay. Range space include all the images of all the points inside the domain. Okay. Means you have suppose 3 points inside this 1, 2, and 3. They are mapped with some 5, 6, and 3 is also mapped with 6, and here 7. So the codomain is 5, 6, 7, but the range space is only 5 and 6. Okay, range space include these 2 points only, not this 7, because 7 is not an image of any point in this V. So this is the range space. Okay. And now if it comes to kernel, so kernel is basically suppose these two are mapped with 0. Okay, 0 vector is also there that is mapped to 0. So kernel space will include these 2 and 3. 2 and 3. So 2 and 3 are basically in this vector space, and 5 and 6 are basically in this vector space. Okay.
So basically, image space means the vectors which have image that will come
Yeah.
inside the image space. So it is the vectors in the domain or vectors in the codomain in image space.
These are the vectors Codomain. They are images that we are storing.
Okay, okay.
We are not storing the point itself. We are storing the output.
Output. Okay.
Okay.
Sir, image is the range set, no?
What?
Yes.
Image is the range set or codomain.
Yeah. Okay. So now let's move. Okay, kernel or null space, it is given that it is also a subspace. Image or range space is also a subspace, vector subspace of W it is, and it is of V. It is of V, it is of W. Okay. Dimensions of kernel or null space transformation is defined as nullity. So dimension we can also define as nullity, nothing but the dimension of kernel space. Okay. And dimension of range space is nothing but rank of T. Okay. After that, T is an injective linear transformation that is done. Surjectivity is done. Okay. Any n-dimensional vector space it is done. Okay. Matrix we have found that how to write a matrix of a linear transformation. So what do? We actually find out with respect to some basis. We take some basis here and we find out its transformation and we define this transformation as a basis of W. Okay. As a linear combination of basis of W. Okay, and after that we got it. So we write these coefficients of rows as columns and yeah, like that. So this will be our linear transformation matrix. So here you can see we are given some transformation here like in this form, and after transformation we are using this basis. So the transformation of these bases is 2 comma 0 and 0 comma 1. So we expressed it as a linear combination of bases of W. So basis we are considering for both and domain and codomain, we are considering the same basis 1 comma 0 and 0 comma 1. So we explained it as a linear combination of these two vectors. Okay, after that what we did, we wrote this 2, this 2 over here, and this 0 over here, and then 0 over here and 1 over here. Okay, make sure that this first row will become the first column of the matrix and second row will become the second column. Okay, so here are some other examples are also given, so let's leave them. Okay, it is done. After that what do we have
R3
here?
to R3 transformation is
What?
R3 to R3 transformation. I saw the one of that
Okay, R3
above.
to R3, so there is no. Okay, let me see. uh, Here it is. Where is this? Yeah, here it is. So this time the basis will have three vectors, right? Okay, so three vectors are there. So what we did, we transformed first vector, we got the transformation. We transformed the second vector, we got it, and third we got it. We have to use as both domain and codomain here. No. Puts ordered basis of R3 for domain and dash for codomain. For codomain, we have to use the standard order basis. Okay. So that's why we are explaining it as a linear combination of these three vectors that are inside the standard order basis. So we got 1, 5, 3 coefficient. We wrote it as first column. And here the second row is as second column. And third row we have as the third column. Is that clear?
Sir, standard ordered basis is same as standard basis, right? I mean, what?
Yeah. Standard ordered is that same thing. Yeah.
So
Okay.
why
Standard
we are
order
writing
means
like I have one doubt, sir.
what?
In T110, when we taken the above ordered basis, then we are writing
Yeah.
it as a combination of one, then combination of 100, 5, then
Yeah.
010, then 3001.
Yeah.
But in the
Yeah.
T part in the left hand side, it is 110.
Because we have to use for domain we are using this basis. Okay, for codomain we are using standard basis. So when we are transforming, so we will use the domain basis to transform, and we are when we are writing the linear combination of codomain, so we are writing it as its a basis.
What is standard basis then?
Standard basis means this uh, when we give only one value to one component and other values will got zero, other components will get the value zero. Okay, like this. Then next time we will give the second component as value one and all other will get zero. Next time third component will get one and this one, like this, 0 0 0 1. So this is the
Okay,
standard
put one as
ordered basis.
okay, we put one as a value for a x particle, then to the zero
Yeah.
zero, and likely to be on all x y z's.
Okay, let me explain it a little bit. So what was the problem? Why do we said this standard and the others are not standard? Because suppose you have a two-dimensional plane over here. Okay, and I tell you that you have to go somewhere in this point. So you require two different direction. One is suppose here and other is here. Okay. So if you want to go to this point, so in which way you go? You will go firstly here using this direction, and after reaching here, you will go using this direction to this part. Okay. So this is a way of going. But suppose if your standard bases are there, so you will have this direction and this direction. So if anywhere you have the point, you can directly go there without even worrying about, because firstly you will move in the one component direction, that is nothing but 1 comma 0 direction, and this is nothing but 0 comma 1 direction. So we are considering the axis is full direction. So that's why we call them a standard basis. In this case, the what was the basis? 1 comma 1, and it is nothing but minus 1 comma 0. So these two were the bases here. So for standard, we consider these positive x-axis, y-axis, and z-axis, and so on as our standard components for the further analysis. Okay.
For every further analysis, we have to just go to standard order basis. Like if we go to R2 to R3 transformation, R1 to R3 transformation, then every time we have to go with the standard order basis.
No, if it is if in question, if it is given that some manual or other ordered or other bases are there, so you have to use them. But if most cases we use the standard one because it is the easier one to understand.
Okay, sir.
Okay.
Sir,
Now let's move.
sir, so this
Yeah.
matrix representation of T. So can you just, yeah, this matrix representation of T,
Yeah.
this is basically the coordinate vectors, right?
This is not the coordinate vector.
153 minus 1 4
Sir,
6.
instructor, sir,
You can write
so that
because
this is coordinate.
when you are when you are using the standard basis, so it will be a coordinate vector, you can think. Okay, but if you are not using standard, then they are not going to be.
Sir, coordinate vector means sir has told that linear combination that like you are telling no, that is the linear combination and
They,
coordinate vector are same.
means, sorry, that
The
means
coefficient.
This coordinate vector, please.
Yes, sir. That linear combination you're expressing na alpha, beta, gamma. That
yeah,
is that is the coordinate
Yeah,
vector.
that is the coordinate vector, right, sir?
yeah,
Sir,
right.
See, yeah.
So let's move.
sir, I
Okay,
have a
here is
problem
fine.
in 1 and on 2 that how to find that.
What do you want to find?
If the transformation is 1 1 or on 2, how to means verify that.
Okay, one and on two.
Yes,
So
sir.
for one you can verify to put any arbitrary vector. Suppose you have x comma y comma z, and you can equate it to zero vector. You will find all those points which are mapped with the zero vector of W vector space. Okay.
Yes,
So
sir.
you can find all these points of all the solution for this. If you found more than one solution, if it is not unique solution, then you can say it is not injective. Okay, injective.
Sir, can't we
And
say
if you
that
found
zero from domain should map to zero in the codomain?
it will all zero vector mapped with the zero vector of W vector space. Okay, but there are
Yes.
some other vectors as well then that can also map with this. It will always map, but there are some other vectors as well
Okay,
that can
okay.
map it if it is not
Correct,
in.
correct, correct.
Okay. So in unique case, if it is, then you can say it is injective. Only the zero vector is mapped, other vectors are not there. Okay.
Yes,
Means
sir.
if this implies that x is equal to y is equal to z, only this. For onto, you have to check the range space and codomain space are same. Means any point, is there any point inside the codomain that is not inside the range space, then you
So
can say it is not
definition wise,
onto.
it's clear, sir, but in problem, how to apply that part?
Okay. Suppose you are given a transformation of x comma y that is mapped with x comma 0, right? So
Yes, sir.
it is from R2 and it is from R2 here. Okay. So now if you observe here that it only consider those points which have the coordinate y as 0.
Right,
It
sir.
is not considering all the parts. Or what you can think that here you have only one variable here. So one independent variable is there. Okay. And the dimension of this vector space is 2. So automatically one dimension is there and one is lost. So one lost is there. So means there are some points that may not be an image of the points inside this domain. So you can consider that minus 1 comma 1 is inside this R2, but it cannot be written in this form. We can't write like this. So if we can't write like this, so it is not an image of any point in this domain. So it is not onto. But if you consider the simple relation like this x comma y, and this is nothing but twice of x comma y. So here if you take any vector, suppose you are taking some a comma b, so you can write it as 2 times x comma y, right? So what will that be? So you will get the value x is nothing but a by 2 and y will be nothing but b by 2. So means if you write, if you have a range, if you have a point in the codomain in this form, so you can get the its image, it's a pre-image, sorry, by dividing its component by 2. So for every point in this form a comma b, you have a pre-image such like a by 2 and b by 2. So there is no point left. So that's why it is onto. Okay.
Yes, sir.
So next was
Sir,
finding basis for null space. Yeah. Yes, Mayur.
sir, above point, above one, what is that written? Like, no, sir, downside. The kernel image and this part. What is that
Okay. Here
means?
we are finding a basis for this. Okay. For kernel of t, we are finding here. You can see the method are given below it. Okay. Some easier methods. You can see here we are given transformation like this x comma y is equal to x comma 0. So you can see that this image x is what is x? X belongs to real number, right? Y is also belonging to real number. So if you look at this range is covering all those points that are in this form x comma 0 means real number comma 0. It is covering all of them. So for this, if you want to write a basis, you can, how can you define this basis for this x comma 0? You can write x times 1 comma 0, right? So this vector 1 comma 0 is can span the image of t. It can span image of t. Now for kernel of t, so what do you want, how to find the kernel? So transformation of x comma y should be equal to 0 comma 0, right? So what is transformation? It is x comma 0 is equal to 0 comma 0. So from here if you compare, so you got x is equal to 0, but what about this variable y? So all these points in this form 0 comma r are the kernel points. Okay, so how can you find out, suppose all the points not are, let's write here 0 comma y where y belongs to real number. So how can I write the basis for this? 0 comma 1 times y. So all the point in this form are inside the kernel 0 comma 1.
Sir, can you explain once again this part, please?
Okay, just a minute.
Sir, it is not 1 1, no? Because the kernel is so many.
It's not one. Yeah. Because there is kernel existing, so it is not injective. Okay. If I want all the points for which all the image points that are inside the range space, means all those points that are inside the range space. So what is its range? Range is nothing but x comma 0. What is x? X is here. You can see it belongs to R2, means x is any real number. Okay. So all points in this form are inside your range space. So you can rewrite it as like this x 1 comma 0. So it is nothing but a linear combination of this vector. So you can define that image space is nothing of T. It is just a span or all the linear combination of 1 comma 0. Okay. Now for kernel, you know that transformation of any vector, if it is mapped with zero vector, so it is inside the kernel space. Okay. So if you find out all those vectors, means the transformation of x comma y is equal to 0 comma 0, those vectors. So what is transformation of x comma y? It is nothing but x 0, this one is equal to 0 comma 0. So second components are matching, so means okay, solution exists, and x is equal to 0 is given. Okay, means all those points for which the x component is 0, y can remain same. So 0 comma y, all those points of this type. So from here you can rewrite it like this, y times 0 comma 1, where y belongs to real number. Okay, it is nothing but a linear combination of this vector, right? Or scalar multiple of this vector. So you can write span of 0 comma 1 is going to be your kernel space. Is that
So,
clear?
so basically, sir, this is the null space or what?
Yeah, this is null space, kernel space. Okay.
Okay.
Next is finding basis for null space. How do we find out basis for null space? By using reduced row echelon form. Means by firstly finding out the matrix, okay, the matrix representation for any linear transformation, and then using that matrix to find out the basis for null space. So you can see here we are given a transformation from V to W. After that, we have to find out some standard ordered basis where beta is given like this and gamma is given like this. Okay. Then use row reduction to obtain the matrix R, which is in the reduced row form. So firstly, we will find out the matrix representation. Then we will reduce it to the row echelon form, reduced row echelon form, RRE form. Okay. So inside this, so finding the pivot and non-pivot columns, you will find out the pivoted columns and non-pivoted columns. Okay, so the columns form a basis for null space of A precisely when the vectors okay belongs to, okay, so get a basis for quantity for okay, Rx equals 0 we did. So x is basically all those points for which the transformation is giving us 0 vector. Okay, so from this we will find out all the non-pivot elements. Non-pivot will form for the will go for the image, sorry, kernel space. Kernel space, right? And the pivot elements will go for the image space. Let's see one example. Here you are given a transformation. You find out a standard with respect to standard basis. You find out the matrix. Okay, then you reduced it. After that, what we did, we find out. We wrote it in this form: Rx equals 0. Okay, we found that we can write x1 is a dependent variable and x2 is a dependent variable. So we wrote it in the form of x3 and x4. Okay, so the null space is nothing but we are going to give first variable value 1 and other one will get 0. Okay, next time this will get 0 and other one will get 1. Okay, so we defined these value x1 and x2 by these equations. We got it. So we got this as a,
Sir, why we got that 1 and 0 and 0 and 1 in the
because we
last?
use use standard value for independent variables. There is no fixed value found for in these independent, okay, because they are free variables. So we gave them value by our side. So it is quite obvious that you can give the easier values like 1 comma 0 comma 0 and then 0 comma 1 comma 0 like this. So we usually give this.
So,
It is some
sir,
standard.
sir, can you
Yeah.
please explain this on the null spaces spanned by the vectors minus 9, 3, 1, 0, where?
Yes, how this
What?
9 3 minus 9 comma 3, how it that come? We just added 1 comma 0 and 0 comma 1 by our like
You
Steps.
got x1, listen, you got x1 is nothing but minus x3 minus 2x4,
Right.
right?
Right.
Okay. x2 is what? x2 is nothing but 3x3 minus x4. Okay. And you are not aware of x3 and x4 value and
Okay. Okay. Okay.
no
I
relation
understand.
between these two.
Okay.
So
In
if you
one
give
we
1
have
and
we,
0,
we have put 1 and 0, and another we have put 0 and 1. Right.
yeah, minus 9 you will get from here. And when you are going to put the value as 0 comma 1, so if you put 0 comma 1 here, so you will get minus 1, and here you will get minus 2. So these two are the vectors that you got, right?
Okay. So we have used the standard basis vectors only for this one also. One
Yeah.
zero and 0 1.
Yeah. Okay. So
1 comma 0 and 0 comma 1 are put by like x3 and x4, and x3 and x4 part, uh, yes sir, there 1 comma 0 and 0 comma 1 is put like as a step, as we have to do that. It's not by any calculation.
which one?
He's getting
Can
confused.
you please?
Why are we taking value x3 as 1 and x4 as 0?
Okay, this one. This is some standard. It means suppose we have some independent variables. 3 and 4 are independent because without pivot elements they are okay. So we give these values like this. Suppose you have n independent variables. So firstly, you will give the first independent variable as value is 1 and other will get 0. Okay, next time what you will do to find out the next vector inside the basis, you will give the first independent variable 0, next one will get 1 and other will again get 0. Next time, first two will get 0 and third one will get 1 and so on. Next one will get 0. Okay. So in this way we continue. For these n independent variables are there. So we require n vectors to span the kernel space, right? Is that clear?
Yes, a little bit.
Here listen one thing that this pivot columns can form this, but non-pivot columns are not the kernel space. They are something else. Non-pivot columns are not kernel space. Okay, we find out the kernel space by finding out a basis like this. Okay, this pivot columns form the image space. So directly, if you want a basis for range space, so you can see that first column has the pivot, second has pivot. So pick up the first column and pick up the second column. So this vector first, this is second. It will form the basis for range space. It will be a basis for range space. You can see this one. For kernel space, you have to give values like this and so on. Then you have to find out the vector. But for range space, you can directly find out.
So then
Now let's move on.
why has it been written like non-pivot space? Non-pivot columns will be kernels.
Non-pivot elements. Okay, non-pivot elements actually tell you that how many vectors will be inside that kernel space. How many means minimum how many linearly independent vectors you require in order to span this complete kernel space. So that's why I wrote here that
Okay.
non-pivot elements can tell you the number of.
Okay.
So
Can tell me the
it will
number
give
of
the
Minimum.
nullity.
nullity.
Yeah, it
Correct.
will give you the nullity.
Nullity.
Nullity directly. Okay, you don't have to go for finding basis and then calculating. You can directly write. That's why I wrote. Okay. There is next rank nullity theorem. So what does it state? It says that rank of T plus nullity of T is equal to dimension of V. Okay. Oh. Is anything else remaining? This is the last part, I think. Yeah, it is last. These are similar matrices and these things is in your week 7, right? Equivalency and similarity of matrices. Or in week 6 they are.
Week 7 only, not 6.
Week 7. Okay. So not in 6, then that's enough. Okay. So let's see here rank nullity theorem. What does it state? It says that rank of T plus nullity of T is equal to dimension of V. So rank of T is nothing but suppose you have vectors in R3, okay, and one dimension is actually going for nullity, one. So remaining two can go for the rank. They can form the image space of themselves. So these two can go for the uh, range space. Okay, and this one goes for the nullity. So if I add these two things, so I will get the dimension of this one R3. I will get.
So nullity is the kernel space, right?
The nullity is the kernel space. Kernel space means the basis cardinality of the basis of kernel space. Means if I want to span, so how many minimum vectors I require, minimum linearly independent vectors I need to span this complete kernel space. So it will tell me the number of these vectors, nullity. Next is given here, if linear transformation is injective, then rank of T is equal to dimension of B, because nullity will be 0 in that case.
Yes.
Okay, so rank of T will be directly equal to dimension of B. Next is, if it is isomorphism, means both
1 1 and on 2.
onto, yeah, onto and 1 1 both. So dimension of W. So whatever be the dimension of W, suppose I have a R3 point here. So all three will go for the range. Okay. And
Yes.
if all three are going, and here all the points inside this R3 uh, are some image of these points inside this R3. So we can say that dimension of W, this 3 is mapped with this 3. Dimension of W will be equal to dimension of B. Okay, even if it is a point in R4, so only 3 dimension will be get covered and one will remain. Because we have 3 independent here, so only 3 can go here, remaining will be lost. This one will not have any effect. In that case, but it will become, what it will become? Uh, it will not be on 2 in this case. So that's why R3 will be there. If it is isomorphism, means all the points inside this part is an image of points inside this. So their dimensions should match. Okay. Next is finding rank. How do we find rank? So here we are given x comma y is mapped with this part. Okay. So firstly, simply we can find out the rank in these cases. We don't have to go much for finding matrices and doing that calculation and so on. You can directly see it is nothing but 0 comma x. So you can put x outside 0 comma 1. So it can be spanned by this vector, right? Now for kernel you want to go, so you can directly write transformation of x comma y is equal to 0 vector, okay, of R2. So what is 0 vector of R2? It is 0 comma 0. You have to compare it with transformation of x comma y. That is nothing but 0 comma x. So first component is matching with first. Second you have to match. So x value is you contained as 0, okay, constrained at 0, and the y value is still free. So you know that all the points in this form 0 comma y will be inside the null space. So you can rewrite it as y times 0 comma 1. So this 0 comma 1 will span the kernel space. Now rank and nullity you want to find. So you can see that inside the basis of this image space, you have one vector. Inside this, you have one vector. So 1 plus 1 is equal to 2. 2 is the dimension of this R2.
So,
Where is this?
so this x 0 comma 1 is a part
Yeah.
of rank nullity theorem. Like x 0 1 is a rank, or 0 y
No, no.
0 1 is nullity.
Sorry, I'm not getting.
Sir, if the question says to find rank and nullity, we need to
Yeah.
find range and kernel respectively, right?
Yeah. Yeah. Right.
So rank and kernel is nullity, right? So what we did is
Rank and
finding x is 0 comma 1 is a span of rank.
yeah.
All right.
You can
And
think
the
it
kernel
is.
kernel we did is kernel point we did y01. So that will
Yeah.
be like the nullity.
Yeah. It is
Yes.
nullity.
Nullity is 1.
Both are
Uh, and rank is also 1.
rank is 1. So if we add these two, we got 2. That is the dimension of V, the first vector space or the domain vector space. So here it is R2, this one, domain of R2, right? You are given that V to W is a vector linear transformation. Dimension of V is given as 5, means this V has dimension 5 and W has dimension 7. Okay, and T is 1 1, means for every point inside this V, so have an image inside this W. So five linearly independent directions are there, or dimension is there. So it can take maximum 5 out of this. So 2 will remain here. Okay. So from the rank nullity theorem, what we can say that what will be the rank of this transformation? Rank of this transformation. So no dimension is lost because there is no kernel space. No kernel space. Okay, so all these 5 dimensions that we are taking to find out the range, so all 5 will have some range. So 5 will be covered there. So the rank of transformation is nothing but 5 in this case. Okay.
Answer D. Answer the remaining two will be the null space. Nullity, right?
No. W is not going to go for nullity. It will remain. It will tell that it is not on 2 because 2 are remaining, not on 2. For nullity, we check the domain space only. This one we check for kernel space or null space. This W is telling us surjectivity, or it is for injectivity side.
Okay. For kernel, we check only the domain side. Okay.
Yeah, domain. That domain is having, is there any vector that is mapped with zero vector or not? Any
Okay. So
non-zero vector that is mapped.
this is not injective, right? This is onto.
Yeah, it is not. It is injective. It is given. It is
Okay.
not surjective.
Okay.
It is
Sir, if I
injective. That's why all. If
sir,
it
if we
is
say
not injective. Yeah.
sir, if we
Yes,
say
my.
like vector is like 5 and
Okay.
like our vect and W is 5, then it will be on 2.
Sorry. If dimension is 5 and W dimension is also 5, right?
Then this is on
So
2,
yeah,
na?
you can. Yeah, then you can say it is might be onto or may not be. It is still possible.
Why, sir? Maybe.
Really
Okay,
depend
let me
upon
tell
your
you. Suppose
transformation function. No?
it depends on, yeah, it depends on the transformation function. Means suppose you have x comma y. Okay, so R2 is there. Okay, and R2 is also there as W part. So its dimension is 2, its dimension is 2. Okay, so now if you transform this, so in the earlier case we transformed, so we got this. Okay, okay, let me think this. Okay, if it is not matching, yeah, right, it will be 5. Correct. Because injectivity is there, so it will be 5. Both will be
Okay.
equal. Okay, if it is injective, then it will be equal to this. Otherwise, it will not be. If it is not injective, then there might be kernel space that can reduce this direction. Okay, but make sure this should not be of 4. If it is of 4, so maximum you can go for 4, right?
So won't it depend
And
upon the transformation function, sir?
yeah, it also depends upon the transformation, that what kind of null space you will have. But you can tell the rank and nullity just by looking at the dimensions. Rank and nullity you can tell directly, but you want if range space and null space, that what will be the basis for these two, then you require the exact transformation. You can see here, let me solve some questions, then you will get it. Okay. Okay, so here you have considered linear transformation like this. Dimension of V is given as 5 and dimension of W is given as 3. So automatically, if even if you want, then still the kernel space 2 dimension will be lost. Because 5 dimensions you are having in V, so only 3 can go for, because dimension of W maximum dimension is 3, so it can only take 3 vectors, 3 dimensions. So 2 will be there or already. And even if it is 3, still we can define some other things that it will only take 2. It is quite possible. Okay, but it is taking 3. It is given already, the dimension of W is 3. So and dimension of kernel is given as 2. So means all the 3 remaining will go for range space. So if all 3 dimensions from here went there, so out of this 3, we got as image for image 3, so all are equal. Okay, so it will be surjective in this case. Onto. Onto means the dimension of range space should match with the dimension of range space should match with the dimension of codomain. Okay, so from here you can see the total dimension we have 5, and for nullity or rank, if I want to find out, so rank will be nothing but dimension of V minus kernel of V. Okay, or nullity of V. Okay, let me use eraser, then it will be easier for you to look for it. Okay, so let's go for the rank nullity theorem again. So what was that? That rank of T plus nullity of T is dimension of V, right? You are aware of this. So now if you look here, what is the dimension of V? It is 5. So 5 will be equal to rank plus nullity, right? Nullity is given as 2. So you can write rank is nothing but 3. You got rank 3. If rank is 3 and dimension of W is 3, it is codomain's dimension, it is range space dimension. So you got both are equal. So it is onto. Is that clear? Anyone still facing issue? You can ask.
Yes, sir, it's clear.
Okay.
Sir, in that one example, let's say if in my transformation is not transforming my zero vector to of u v to zero vector of w, that in that case it fails, na sir, whether they are having same dimension or not. One
Sorry,
one
I didn't
fails.
get
Sir,
one.
for the
Listen.
transformation from v to w, yeah, one. Even if they are
Okay.
having same dimension, v and w, if the zero
Yeah.
of v is not mapping to zero of w, that entire one thing fails, no sir.
Okay. Let me tell you one thing. That dimension of V is given 5, right? So 5 is nothing but rank plus nullity. Use the theorem directly. Okay. Rank and nullity. So what is nullity here? So it is given that it is 1, 1. So nullity will be 0. So what will be the rank? So rank will be 5. Means dimension of range space is 5. Okay. And dimension of W is given as 7. Dimension of W is given as 7. So
Sir, I'm not
automatically
talking
there are
about
two
this question, sir. I'm just talking about in general, sir. In general, I
in general
got
what?
your point. Okay, let's say that I have a transformation from V to W such that dimension of V
Okay.
is 5 and dimension of W is
V
also 5.
is 5 and dimension of W
W
is
is also 5.
5. Yeah,
But my
5, right?
transformation is such that the zero of V is not mapped to zero of W.
0 of V is not mapped to 0 of W. No, it is
Yes.
not going to be. It should be there. It is to be mapped.
So if it is not mapped, then it is not going to be 1 1.
1 1.
Correct, sir?
If it is not mapped with this one, then it will not be a linear transformation. Okay. If the zero vector of this vector space is not mapped, then it is not a linear transformation in that case. It is strictly to be followed that the zero vector mapped to the zero vector of this.
So this is a
Always
mandate.
it is.
So this is a mandate basically. TV equal to 0 for V equal
Yeah.
to 0.
Yeah, for every time. There may be other vectors also that are not zero vectors and mapped to this zero vector of W space. But this is always going to be mapped.
If it is
Okay.
mapped, then it will be onto now.
If it is mapped, this vector or this one.
The dimension of W is 5 and vector V is 5. Then it is
Yeah.
onto now.
If it is 5, no, it is not onto. It can be not onto, because suppose out of this 5 dimension, one is going for nullity. So only 4 go for range space. So here we have 5, but we got only 4. So 1 is still remaining. So it will not be onto.
How we can say it, one has been gone to, only one has been gone to there.
One, I am saying that for nullity, suppose for nullity, maybe other dimensions are also going for nullity, but suppose if only one gone. So let me give you an example for this. X, suppose the point is in this form A, B, C, D, and E. So I transformed it to A, B, C, and rest two are zero. Two dimensions are gone for nullity. Okay, D and E components. So their respective dimension gone for nullity. Okay. So in this case, you can see that this whatever this is, this linear transform. Its linear combination can form uh, only those points for which this fourth and fifth components are zero. So we can take it from R5. So what about those points for which these last 2 points are non-zero values? So 2 dimensions are still remaining, and only 3 are covered here. So image space is 3, and the dimension of codomain space is 5. So that's why it is not onto. We can say that 1 comma 1 comma 1 comma 1. It belongs to R5, but it cannot be it cannot be an image of any point inside this vector space V, because it is not possible. We have only image spaces point as where the fourth and the fifth component are zero, right?
Sir,
Yeah.
so basic, I'm not talking about this. So earlier, like, we were discussing about this thing, right? That, the zero component in vector V has to be mapped to zero component in W, for example.
Yeah. Yeah.
Yeah. But in this case, like, when we define a linear transformation to be valid, so like we have two things, right? TU plus V equal to TU plus TV, and T of
Yeah.
CV is C of TV, right?
Yeah. Yeah.
But sir,
Right. Exactly.
in that case, sir, why we are not in, and this is just coming to my mind, sir, in that case, why we don't include this thing also, T of V equal to 0
Why are
for
we
0 to 0
sorry? What?
transformation.
0 to 0?
0 to 0 is mapped or not? Right.
Yes, sir.
Yes, yes,
We
yes.
never
Why
talk
do
about that condition, no, sir. We
we don't
just
talk about
get
that condition, right?
addition and scalar
Scalar
multiplication just to prove.
multiplication, we only talk about that.
Okay. Why are we not talking about the scalar
Yes, yes,
multiplication is valid
yes.
here or not?
No, no, no,
Yes.
Okay.
sir. When
No,
we talk about linear transformation, we only talk about addition of two vectors
I'm not.
resulting
Yeah.
in a vector in the codomain, and
Right.
linear combination and that scalar multiple of domain will result in a vector in codomain. But we never talked
Right.
about that zero vector in domain directly
Mapping to
mapped
a
to zero.
zero. Yes.
So zero vector is mapped with zero vector. It is
Uh,
not we have talked about
yes,
subspaces,
sir. I
right?
think maybe I might have missed.
Because we don't talk about in
Okay.
the in for a linear transformation to be a valid, right? We specifically
Okay.
talk about that addition and the scalar multiplication only. We never talk about that. I think so. I'm
That
not
means first we go for the zero vector that you said. Firstly, let's take that zero vector.
Yes, sir. Yes.
Okay. Firstly, let me solve for this. Where was that? It was given somewhere. Is okay. Here it is. Image of a zero vector is the zero vector of W. You can see that transformation of 0 plus 0, I can write it will be same as transformation of 0 plus transformation of 0, right? I can apply the transformation individually on both. And 0 plus 0 is nothing but 0 vector again. 0 vectors, they are V. Okay. So if I add these two, so it will again be a 0 vector. Transformation 0 vector is equal to transformation of 0 vector trans plus transformation of 0 vector. Okay. So
okay.
if I do using the cancellation law, if I add both sides transfer 0 vector and here, let's not add because it is not going to change any attributes here. It will be same as means if we add 0 vectors, then it will have no impact. Okay, right? So if I cancel these two values, so what I got, transformation of 0 vector is equal to 0, right?
Okay. Got it. Okay. This is a proposition. Okay.
So this is just addition law which we are looking into now with respect to zero vector, but we have never said that zero map to zero. Okay, maybe the result of this is taken as a rule. We can.
This is a derivation.
This is a derivation. You can see that zero vector of V is mapped with zero vector of W for all the transformations, linear transformations.
Okay.
So it is a proof for that. The transformation of zero vector will be equal to the the zero vector of a W vector space, right? So what was the other doubt? Or is that clear?
Yes, sir. Yeah.
Okay. So after that we have seen this thing. So let's move. Okay, so here we are. So this one we have done. Let's see. Yeah, this one. Validate the statement. There is a linear transformation R4 to R3 with kernel having only this zero vector. Okay. So R4 to R3 we want to go. Okay, so we can go. That's fine.
So when
And
we say kernel has zero vector, so we are saying nullity is zero, sir.
yeah, in this case, nullity is zero.
Okay.
So in this one, it is saying that it is not possible, right? Why is it not possible? Suppose you have 4 dimension here and 3 here. So you want to go, V has a dimension 4 and W has a dimension 3. So out of these 4 dimensions, you can only provide 3 to there. So where will this one go? It will go for null space, but it is saying that no, the null space is having only a zero vector, means dimension of kernel space is 0.
Basically.
So it is not possible. Where will this one go then? It
Okay.
can only take 3 dimensions. Okay. And 4 dimensions we are having here. So only 3 we can send here. Where will this remaining one will go? It will go for null space. So that's why kernel can't only include this. It must include other vectors as well. Okay. So here we have to validate this. So that's why T cannot be 1, 1. In that case, hence the statement is false. Next is this. In this one, R3 to R2 is given. Okay,
Sir.
right? Yeah.
Sir, in the previous question,
Yeah.
uh, so when we said that we were moving from R4 to R3, isn't
Yeah.
it possible? I mean, I'm getting a bit confused over here right now. If it is an onto mapping, will it still the same thing will happen?
It is onto, but it
Mhm.
is not 1, 1 in this case. Okay, it
Correct.
can be onto, suppose x plus y and y plus z is there,
Mm-hmm.
right? So it has 3 dimensions. Only two will go there, and remaining one will cause form the null space or go for the kernel space.
Okay.
Okay,
Okay.
so from here you can, it can be any real number, it can be real number, and it is of R2 point. So 2 dimensions are covered here. And here we have a 3 dimensional points. We are taking R3. So 3 dimensions are there. So 2 go for there and 1 will remain for the null space.
So, sir, basically, dimension of my image space will be 2, basically, right?
In this case, it is in this case when we are taking these two values, then it is
Right, right.
dimension of range space is 2, right? But
Range
if
space,
I
yes.
took x comma x like this, so
Then
now
it
the
will be
dimension of space
Image
is
one.
1.
1.
Now 2 will go for the null space.
Space.
Yeah, null space of one, yeah, or 1 will go for the image space. Okay. So here are some questions left. So let's see them. Uh, which one of the following correspond to the linear transformation with respect to standard ordered basis? We have to take for R3 and standard order for R2. So here is a transformation given above, like this. So similarly, we will use the transformation of 1 comma 0 comma 0. So it will be nothing but 2 and 0. Okay, next time I can rewrite it as 2 times 1 comma 0 plus 1 0 times 0 comma 1. Right. Next is this one, transformation of 0 1 0. What would that be? This is going to be 0 comma
0,
4, right?
comma 4. Yes.
So 0 times 1 comma 0 plus
4
4
times
times 0 comma 1.
0.
Next
Sir,
one is nothing but, yeah,
sorry to interrupt you again. So I'm coming back to
okay.
the same point. So basically, the coordinate vectors we only form with respect to the. It is only formed with respect to the standard basis, right?
Yeah, yeah,
In
yeah.
this
Then
question,
only.
it has been asked in that way. Otherwise, it has to be any basis. It can be any basis.
Sir, domain is the transformation which we are using, and the codomain is the standard order basis.
We
In
are
this question, sir, we are
No,
using that
both we are
standard
standard
basis.
order.
No?
Both way we are
In this
using
one,
that.
we are using standard order, but on ordered basis also we can form the coordinate vector, right?
Yes, yes, yes.
Yeah.
Yeah. Okay. I was thinking only for the standard basis only we can form. Okay, fine. Got it. Got it.
So, yeah, that's okay. So transformation
sir,
of 0 1 1. Yeah.
R3 is T100 and R2
Yeah.
is 2 comma 0. Then we are writing standard order basis for on the basis of R2.
Yeah.
If I have
R2.
to, yeah, if I have to do like R2 on the left hand side, if I say T10, and we have to transform it to a standard order basis for R3, 4 comma 0 0 4 comma 0 comma 0. So my answer would for standard order basis will be 4100. Okay, understood, sir. Very well, sir. Yeah, understood. I'm clear.
Okay. So this one is given here, T001. So you can put the Z value as 1. So it will be 3 and it will be 1. So it will be 3 comma 1. So if I form the matrix now, so my first column will be 2 0, next column will be 0 4, and next column will be 3 1. So where is this matrix? Here. Okay, next it is saying that which of the following represent the basis for kernel. Now you have to find the basis. Till now we are finding only the nullity, so that's why dimension was enough. But now we want basis. So using this. So how can we find out? Firstly, reducing it to the reduced row echelon form.
Sir,
So R1 divided by 2.
would you mind explaining this one once again? The this one. Yeah, yeah, yeah.
This
One question number one.
transformation.
Yeah,
Okay, so what I did, I have to find the matrix with respect to the transformation.
correct,
Okay, so I took matrix. In matrix, what we do, we transform all the standard basis vectors
correct,
of V to we got some transformation here, and we will express these transformation as a linear combination of the basis of W. Basis of W. So we
correct.
got 2 comma 0. I explained it as a linear combination of these two.
Right,
Okay, I got. So now whatever be inside my first row's coefficient, so I will use at first column.
correct.
Next 0 4 I used here, and
Right.
3 1. You know that can be written again 3 1 comma 0 plus 1 times 0 comma 1. Right. So 3 and 1 are there. So I wrote 3 1.
What's a 3-1
So
like?
this is my
3-1
From
how?
where,
3-1. Same question, 3-1 how?
from where did we get this 3-1?
3 1. When you are transforming this one,
Oh,
x value is 0, y value is 0, z value 1. Here this one.
okay, 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 okay.
Okay.
This is the third basis transformation. Okay, okay, got it.
Third basis because it is of R3, so we require three
R3,
vectors
R3.
there.
Okay, okay, okay. I was focusing only on the first two. Okay.
So now let's
Still
move on. 1 0, yeah, 103 by 2, and R2 if I divide by 4, I will get 0, 1, and 1 by 4, right? And if I took both the all three variables x, y, z is equal to 0 comma 0. 0 comma 0, right? So I can rewrite, I can form the equations from this. So what will be my equation? X plus 3 by 2 times z is equal to 0. And the second equation will be y plus z
1
by
by
4 is equal to
0.
okay. So now you can see in basis, all the bases mostly we are using z value as 1. So I can give value of z as 1. It is linearly, sorry, it is independent variable, independent, this one. Pivot elements here, here, and here it is now. So if I give here value 1, so what will be my y value? Y value will be minus z by 4, minus 1 by 4 means, okay, y value is minus 1 by 4. And if z value is 1, so x value will be minus 3 by 2. So minus 3 by 2, minus 1 by 4, and 1. So this is going to be my basis. Okay, so this option is correct. Now once check it for this one as well. When z value is 2. Okay, so simply you can multiply it by 2, or you can put the value of z2, then you can find out from here. So we can simply multiply because linear combinations are possible. So 2 minus 1 by 2 and minus 3. It should be this. But this is not. Here 3 by 2 is there. So that's why it is wrong. Only option 2 is correct. Okay.
Sir, what you did in the
Now it
last
is
step,
R.
sir? In the last step, sir, what did
What?
you? How did you confirm that
In this
option 3
one.
is not correct?
Okay, we put the z value 2. Okay, you can put z value 2. So what you will get
Okay, in
x
the
and y
equation.
value, you
Okay,
will
okay,
get
fine,
these two.
fine, fine.
Or you can simply do multiplying by it by 2 because z value you need to make 2, so you can
Yes, yes.
multiply it by 2. But if suppose many other vectors are there, so then maybe it is having only one independent variable. If more than one are there, then you have to put all the linearly independent variables value from here in that basis to get check the answer. Okay,
Yes, I got it.
we will confirm that next.
Sir,
What will be the
what
dimension of? Yeah.
understood, sir. Sir, what you said
What?
last, that to confirm that it also
Okay.
have some other kernels.
Okay. Suppose it wants to check. Uh, Let me, I will take some example after that. Okay, then I will explain that part. Okay. For now,
Okay,
let
sir.
me complete this question. Then I will explain that part.
Okay,
Okay.
sir.
It is asking for dimension of subspace of image of T. So what is image? Image of T dimension. So you can see directly what is the rank here of this matrix. It has two pivot elements.
Yes, two rankings.
So what will be the dimension? Dimension will be, or rank, not dimension, rank will be
Two.
2.
2.
So answer is 2 directly. Next is this one. Choose the correct option.
Sir,
So
sir,
you can,
sir,
yeah,
sorry. So dimension is also 2, right? In this case, or 1.
in this case, yeah, dimension of W. Dimension we are using with the subspace, so it will be 2. And here dimension of image space if you want, so it will be also 2. Dimension of W is given there. Okay, and dimension of image we found, it is same as rank. These two
Dimension
are same
of
thing.
2, right? Okay, okay.
This one, sorry, this one, not that.
So just by
So
finding
next,
the
what?
just by finding the dimension of transformation, we could say that dimension of image space is that.
Yeah, if you can find the rank, then you can say that it is the dimension of image space directly.
Okay,
Okay.
okay.
Next is it is asking 1 1 and on 2. So you can see that R3 to R2 we are mapping. So maximum this can take 2, and this is having 3 dimensions.
One is
So
free.
2 can go, but 1 will still go for the nullity. And
Yes.
if nullity is there, then it cannot be 1 1. It cannot be 1 1 if nullity is there.
Cannot be 1.
Okay. And yeah, and T is on 2. Why it is on 2? Because dimension of W is 2 and dimension of image space is 2. So they are matching. So we can say that it is on.
So
They are equal.
dimension
If
of W
image
we got from the dimension of that
Trans-
solution space.
R2, not solution space, R2, codomain space dimension.
Okay, okay.
It is the dimension of that whole codomain space from which these points are going to be in which. Okay, so that's
Okay, we are just
next is
equating
this.
range equal to codomain. Okay, okay.
Yeah, yeah, that's the thing. Next is nullity and rank of a identity transformation on a vector space of dimension n and 0 are n respectively. Okay. Nullity will be 0 and transformation, it is saying that suppose you're transforming any vector space V to W, V to W you are applying. Okay. It is of Rn. Okay. Rn, and it is identity, means if you are transforming x comma y comma z, so it will be transformed to x comma y comma z. So you know that it is nothing but 1 1 1, you will get the coefficient. Okay, so when you are going to make the,
This part is
let's,
not understood, sir.
okay, I am telling you. So you can see in this case, if you are having an identity transformation, means this transformation will be same as the point given to it. So this one is the identity. Suppose R3 we are considering. Okay. So we got this. So from here you can easily see that what will be the nullity in this case. Nullity will be 0.
Right.
Yes.
Because if I apply x comma y is equal to 0 comma 0 comma 0, so it has only solution x equals y equals z equals 0. So nullity is 0 in this case. So all the dimension will go for the image space. So three dimensions are there and all three went for the image space. So it is asking that rank and nullity. So nullity will be 0 and rank will be full. Same way for R3 we took, you can take Rn. Okay. You can extend this for Rn. Next one is wrong because it is saying 1 and n minus 1, it is wrong. Next one is saying opposite, rank nullity is n and rank is 0, it is also wrong. And fourth one, it is saying nullity and rank of an isomorphism between two vector spaces V and W are n and 0. Nullity cannot be 0. Sorry, nullity cannot be n when it is isomorphism. Means isomorphism means it is also 1 1. And if it is 1 1, so how can the nullity be n? It should be 0.
So even rank cannot be less than 1. No?
Yeah, you can also say that. So let's go. Fifth one, rank and nullity of an isomorphism between two vector spaces are 0 and n. Okay, it is saying nullity and rank of an isomorphism between two. Okay, both of dimension n are there. Yeah, it is right. Nullity is 0 if it is of Rn and we want all n to be gone for this Rn. Okay. So in that case, nullity should be 0. We can't lose any dimension because we want all the dimensions in our range space. And if range space has n dimension and in codomain is also having n, so you can see it is also surjective.
Yes.
Okay, onto. And in that case, if nullity is 0, so what will be the rank? Rank will be n.
N.
Okay. So it is correct. There cannot exist an isomorphism between two vector spaces whose dimensions are not same.
Right.
It is saying
True.
correct.
True. True.
Okay. If you have Rm to Rn, okay. So suppose your m is greater than n. M has more dimensions than n. So m can only give n dimensions to it, and remaining m minus n will go for nullity. Okay, so it will not be 1 1. Now suppose another case when m is lesser than n. So m can give only m dimensions here, m. Okay, what about n minus m? They will be remained. So if they are remaining, so codomain's dimension cannot be equal to image space dimension because there are some dimensions remaining, right?
Right, sir.
Yes.
So that's why it is right. This option is correct. Okay, now let's move on. How many are 6 and 7? Two questions are more. Okay, let's solve them. Option 1, it is saying that any injective linear transformation between two vector spaces which have the same dimension must be an isomorphism. Any injective linear transformation, okay, between two vector spaces, same dimension must be an isomorphism. Okay. So suppose you have n dimensions here and n dimensions here. So you are doing an injective transformation, any linear injective means none of them gone for the nullity. No one went for the nullity. Okay, all the dimensions went here. So if all gone for the image space, so dimension of image space will be n, and codomain space dimension is codomain space CD. It will be n. So both are matching. So that's why it will be isomorphism. It will be surjective here. So if already injective it is and surjective we proved, so it will be isomorphism. Next, any surjective linear transformation between any two vector spaces which have same dimension must be an isomorphism. Any surjective it is same. Suppose Rn to Rn you are doing now again. So it has codomain has n dimension. It is saying surjective. So means image space also has n dimension, right? If image space is having n, so out of this n are gone here. So remaining will go for null space. So how many remained? Zero. So nullity is
Zero.
zero. If nullity is zero, so it is injective, surjective already given, and injective we proved. So option 2 is correct.
True.
Okay. Option 3 is there. R2 to R3 we are going, and there does not exist any surjective. Yeah, because here we have two dimension and here we have three. If I even if I give all the dimensions for image space, if I give, so it will have two inside the image space. What about the remaining one? It is not covered. The points in this one dimensions are not covered, so it will go. It is will not be surjective in that case
Sir,
because
sir,
they should match image and
sir, can you just explain that option two once again, sir?
option 2.
Yes, sir. Yes, sir.
So in option 2, it is saying that any surjective linear transformation, you have a surjective means the image space dimension is matching with the codomain space, right? N and n. So if you want your image space of dimension n, so you have to take n dimensions from the domain space. So if you took all the n, it is having n, and you want all n for image. So what will remain for the nullity? Zero. And if nullity is zero, so you know that nullity zero implies that it is injective. Surjective already given in the question 2, that surjective linear transformation, and injective we proved. So it is now isomorphism.
Yes, sir. Got it.
Is that clear? Next one,
Yes, sir.
we did that R2 to R3. So one is left. So surjective it is not. There does not exist any injective linear transformation from R2 to R3. Injectivity is followed. Here you can see if we are giving both the dimensions to image. So for nullity remained zero. So if nullity is zero, then it is injective. But it is given here not. But there is
False.
existing. So that's why it is false. It is incorrect option. Okay, now the seventh one. There exists a linear transformation R2 to R2 such that image of T is equal to kernel of T.
No,
Okay.
no, sir. There exists
What does
none.
that mean? What does that mean? Can
If
anyone tell me?
so,
So image is 000 kernel of T.
So,
Yeah,
Null
you have
space.
okay. You have seen the x comma y. Okay, for which we can give the example 0 comma x. So now if you observe here that image space is nothing but 0 comma 1 span,
Right,
right?
sir.
Span of this.
Yes,
Okay.
sir.
And if you want the kernel space, what is it? 0 comma x is equal, sorry, transform all the x and y I want, all the points
Such as equal
for
to you.
which transformation of x comma y is equal to 0 comma 0, right? So if I do the transformation of x comma y, it will be 0 comma x, it is equal to 0 comma 0, right? So x value is constrained to 0. We can take x value as 0. So for this, all these point, x value will be 0 and y can be anything. So if you write, it is nothing but span of 0 comma 1. Span of 0 comma 1, span of 0 comma 1. So here you can see both are equal. Kernel space and image space, both are same.
Right, sir.
So that's why option 1 is correct. Next, there exists a linear transformation such that image is equal to kernel.
R cube
Okay,
to R cube, R3 to R3.
R3 to R3
I
we have
think,
to check.
sir, this is not possible. No?
so false, no, sir. It will be false.
Why? Can anyone explain why? Why image space of T cannot be equal to the kernel space of T?
Because the nullity
You can directly see
nullity
this.
won't be zero,
Listen,
right,
listen
sir?
directly.
Nullity will
You
be
can
zero.
directly see here that it has odd power here. Okay. If its rank I give, rank is supposed 2, so nullity will be of dimension 1.
Yes.
It
One.
can be spanned by it is need two vectors to span, two linearly independent vectors to span, but here you need one linear independent vector to span. So
Correct.
these two are not same. Now if the rank I reduce again by 1, so it will be of 1 and it will nullity will become 2. Again they are different. Okay, if both the spaces are equal, then their dimensions should be equal, right? And in any combination, their dimension cannot be equal, right?
So if it would have been even, then two possibilities. I mean, rank can be
Yeah,
two.
it is possible. If in yeah, in R4 if you are given, so maybe it is possible that in some transformation you will figure out. Okay, the same way
Yes.
in R2 what was happening? R2, one gone for nullity and other one gone for rank, right?
Image space.
Sir, sir, can you explain this one again, please? I didn't get it
Okay.
actually.
It is given that kernel of T should be equal to uh,
Image of.
rank of T, image or rank of T. Okay, right?
Ah,
Image space of T. So their
okay.
dimensions should be equal. Dimension of kernel should be equal to the dimension
Done.
of image.
Correct.
Okay. So what is dimension of kernel? It is basically nullity, and
Hmm.
dimension of image is nothing but image.
Image.
Sorry, the rank.
Rank.
Rank. Okay. Okay. So we know that dimension of V equals from the rank nullity theorem, rank plus nullity.
Correct.
Okay. And if both values are equal, so suppose rank is my R, so nullity will be R as well. So if I add these two, this should be 2R,
2R.
dimension of V.
Okay, but
Okay, so dimension of V should be 2R, means it should be even dimension of
even
V. Okay, but here you can see it
it
is
is odd.
odd given here.
3.
Yeah, so that's why it is wrong. Okay. Next is this one, transformation from V to V is a linear transformation. V1, V2 belongs to V, are linearly independent. Then TV1 and TV2 also be linearly independent. This is false. Suppose you are
Sir,
taking two
why?
linearly independent variables, 1 comma 0 and 0 comma 1. Both are linearly independent, right? Suppose my transformation is nothing but Tx comma y such that it is 1 comma, sorry, x comma x it is. Okay, so what will be this one? This is going to be 1 comma 1, right? And this is
Yes.
going to be 0 comma 0.
Yes.
Okay. So these two are, you can see, one multiple of one another.
Yes.
Okay, they cannot be. Okay, it is only possible to be these things to be linearly independent when your nullity is 0. If nullity is something, then they cannot be linearly independent. Maybe you will find some points that can be written as a linear combination of other one, right? So that's why this is wrong. This is wrong. This is wrong. Fourth one is there, in which V to V transformation is given, means it's the same vector space we are taking, and transformation we are doing are linearly independent. Then V1, V2 are also linearly independent. In this case, let's see. Transformation of V1 is linearly independent with transformation of V2. Okay, these two are linearly independent, means any alpha times transformation of V1 plus beta times transformation of V2 will not be equal to, sorry, will be equal to 0 vector only when alpha and beta both are 0, right? So uh, what I can say, that transformation of alpha times V1 plus transformation of beta times V2 will be equal to 0 vector, right?
Correct.
Okay, so this transformation, this vector is going to be a 0 vector, right? Alpha times V1 plus beta times V2 is equal to 0 vector. Okay, it was only possible when alpha and beta are 0, so it is also possible only when alpha and beta are 0. Is that clear? Is that clear?
Did not get said it will.
Okay.
The
Suppose
transformation it.
I have two vectors. Okay,
Yes.
let's go in opposite direction. Let's try from the back side. Okay, v1 and v2 are two vectors you are having. Okay, you want to check whether they are linearly dependent or not. Okay, one
Yes,
thing
sir.
you need to keep in mind that tv1 and tv2 are linearly independent. So alpha times tv1 and plus beta times tv2 is equal to zero vector only when alpha and beta both are zero.
Right, sir.
Okay, this
Right.
line you need to keep in mind. Okay, don't
Linear
forget this part.
independence. Yes, sir.
So suppose I form some linear combination. I want to form some linear combination. T times v1 plus sorry alpha times v1 plus beta times v2 is equal to zero vector. Okay, I want to find the solution for this. If it is a unique solution, then it will be linearly independent. Otherwise, linearly dependent. It will be. Okay.
Yes,
So
sir.
if I apply transformation both sides, okay, I want to solve. I apply transformation both sides. So what will be the transformation? This one. This will be alpha times tv1, right? Plus beta times tv2 is equal to zero vector.
Right, sir.
So you know that for this equation, we have only one solution, unique solution.
Right, sir.
Alpha is equal
Because they
So
are
that
linearly
more it
independent.
implies that alpha is equal to beta is equal to zero. So if alpha and beta both are
Okay.
zero, then these two are linearly independent, these two vectors, right?
Right, sir. So here we assume that TV1 and TV2 are linearly independent as given in question.
Yeah, as given in question.
Okay, sir.
Okay.
That's the question.
Okay. So any other doubt you are having? Is that okay? Okay. So that's enough
Yes,
for
yes.
today, I think.
Yes, sir.
So let me stop the meeting. So good night to everyone.